Hello friends, welcome to my lecture on finite Fourier transforms. We have seen that the Fourier transform technique can be applied to those problems which involve infinite or semi-infinite domains, like you have a bar of infinite length or you have a semi-infinite strip. Okay. So, there we can apply the Fourier transform techniques to solve the differential equation, partial differential equation. Now, but in many practical problems we often come across finite intervals in boundary value problems. Therefore, we need to extend the Fourier transform method to problems where the range of independent variable is finite. Their inverses can then be found by applying the theory of Fourier series. We know that if a function satisfies the Dirichlet conditions in the interval 0 less than or equal to x less than or equal to L, then its Fourier sine series is given by f x equal to sigma n equal to 1 to infinity b n sin n pi x over L. Let us recall the half range expansions. Okay. When the function is defined over the half range 0 less than or equal to x less than or equal to L, then we can extend this function over the other half, that is minus L less than or equal to x less than or equal to 0, by considering f to be an even or as an odd function. If you consider f to be an odd function, then you will get the Fourier sine series, okay, which is known as half range Fourier series. Okay. So, for half range Fourier sine series. So, there you get f x equal to sigma n equal to 1 to infinity b n sin n pi x over L, and the value of the Fourier coefficients v n is given by 2 over L 0 to L f x sin n pi x over L dx, where n takes values 1, 2, 3 and so on. If you consider the even extension over the other half, okay, over the interval minus L to L, you take the function f to be an even function, then you get the Fourier cosine series, okay, and the Fourier cosine series is given by f x equal to a naught by 2 plus sigma n equal to 1 to infinity a n cos n pi x over L, where the Fourier coefficients a n's are given by 2 over L 0 to L f x cos n pi x over L dx. N takes values 0, 1, 2, 3 and so on. When you take n equal to 0, you get the value of this a naught, and for n equal to 1, 2, 3 you get the values of these coefficients a n's. And you also know that the Fourier series half range Fourier series converges to f x, okay, whether it is Fourier sine series or Fourier cosine series, okay, it converges to f x at each point of continuity of f and to the average of left hand and right hand limits at each point of discontinuity of f. Say the point of discontinuity is x naught, then you have the sum of the series Fourier series as half of f x naught plus f x naught minus. Okay. So, we have to we need these definitions here. Now, let us consider finite Fourier sine and cosine transform. If f x satisfies Dirichlet conditions in the interval 0 less than or equal to x less than or equal to L, then finite sine transform, okay, the finite sine transform is defined as S n equal to S f equal to 2 over L 0 to L f x sin n pi x over L dx. Okay. The value of this, okay, 2 over L 0 to L, no, not this, 2 over L 0 to L f x sin n pi x over L dx. It is defined as finite sine transform, okay. We denote it by S f, or you can also write S n, okay, and its inverse sine transform is given by S inverse of S n. S inverse of S n is equal to S n is S f, okay. So, S inverse of S n is equal to f x, okay. So, S inverse of S n equal to f x is equal to sigma n equal to 1 to infinity, and then we have this S n, okay, S n sin n pi x over L. So, this we denote by S n, okay, then f x is given by sigma n equal to 1 to infinity S n sin n pi x over L, okay. So, in the finite sine transform, okay, the Fourier coefficient v n is replaced by S n actually. S n is the Fourier sine transform of f x, okay, and then the Fourier series, Fourier sine series, okay, half range Fourier series, Fourier sine series is gives the value of the function f x, because now we know the values of S n's, okay. So, this transform is applied when you are given the Dirichlet boundary conditions. Remember, this transform will be applied only when we are given Dirichlet boundary conditions, because they satisfy they specify the value of temperature u at x equal to 0 and x equal to L. This will be clear why we apply the Dirichlet boundary, why we apply Fourier sine transform in the case of Dirichlet boundary conditions. This will be clear later when we consider the partial differential equations. There, when we try to solve the partial differential equation, we will need to take the transform of S u x x, and when you take the transform of u x x, there if you have Dirichlet boundary conditions, you will apply sine transform. If you have Naumann boundary conditions, you will apply Fourier cosine transform, okay, finite cosine transform. So, this is to be applied when we are given Dirichlet boundary conditions. Fourier sine transform we will apply then. Now, finite cosine transform is defined as Cn equal to Cf 2 over L 0 to L f x cos n pi x over L. Okay. So, we have the value of A n here, this A n is replaced by C n r, you can say Cf. Okay. Then this Cf gives the finite cosine transform of f, and f x is then determined from this series. Okay. We have the values of C n's now, this is C naught, A n is nothing but C n. So, this is C naught by 2, and then we have sigma n equal to 1 to infinity C n cos n pi x over L. So, putting the values of C naught and C n here, we get the value of f x. Okay. So, Fourier cosine transform is to be used when we are given the Naumann boundary conditions. Okay. In the Naumann boundary conditions, we have the value of the temperature gradient u x at x equal to 0 and x equal to L. Now, both of these transforms, when you will apply to partial differential equations, they will reduce them to ordinary differential equations. Now, let us see how we solve a partial differential equation using these finite sine and cosine transforms. So, let us consider first an example. Suppose we are given f x equal to 1 over the open interval 0 1. Okay. Then the finite sine transform of f, okay, finite sine transform of f, S n is given by this expression. Okay. Since the domain of definition of f there is 0 to 1, L will be equal to 1. So, we have 2 over 1 0 to 1 f x sine n pi x over 1 dx. Okay. So, we have this 2 over 1 0 to 1 f x, in place of f x we put 1 into sine n pi x over sine n pi x dx. So, S n will be equal to 2 times, let us integrate, you get minus cos n pi x divided by n pi. You put the values, you get 2 over n pi 1 minus cos n pi. Okay. Now, cos n pi is minus 1 to the power n. So, you get 2 over n pi 1 minus 1 to the power n. Okay. Now, when n is even, you get this value 0. Okay. So, when n is even integer, the value is 0. When n is an odd integer, we will have 4 over n pi. Okay. So, 4 over n pi when n is an odd integer. So, S n equal to 4 over n pi when n is an odd integer and 0 when n is an even integer. Now, let us apply the inverse sine transform. Okay. So, inverse sine transform is obtained from f x equal to sigma n equal to 1 to infinity S n sine n pi x over L. So, we can get here. Now, f x is given to be equal to 1. So, 1 equal to 4 over pi. Okay. 4 over pi. Okay. So, this is f x equal to sigma n equal to 1 to infinity S n sine n pi x over L. Okay. So, L is equal to 1 here. Okay. So, we get sigma n and f x equal to 1. F x is continuous over the whole interval 0 1. Okay. So, 1 is equal to, let us put f x equal to 1, sigma n equal to 1 to infinity S n sine n pi x. Now, S n is 0 when n is even. Okay. S n is 4 over n pi when n is odd. So, we can say 1 equal to sigma n is odd integer. Okay. Up to infinity, n is equal to 1 to infinity, but n is odd. Okay. Subject to the condition that n is odd, and S n is 4 over n pi into sine n pi x. Now, if you take n equal to 2m minus 1, okay, then when m is takes values 1, 2, 3 and so on, n will take odd integral values. So, we will have m equal to 1 to infinity, we can write 4 over 2m minus 1 pi and then sine 2m minus 1 into pi x. Okay. So, replace now m by n. So, you get 1 equal to 4 over pi, we can write outside the summation. So, 1 equal to 4 over pi sigma n equal to 1 to infinity 1 over 2n minus 1 sin 2n minus 1 pi x. So, this is how we find the inverse sine transform when Sn is known. Okay. Now, let us see we can solve the partial differential equations. When you solve the partial differential equations, we will need suppose t the time variable, okay, x is the space variable. So, we will need to find the sine transform of sine or cosine transform of ut, utt, okay, ux, uxx and so on. Okay. So, sine transform of ut, okay, sine transform of ut, let us recall that sine transform of Sn equal to S of f we have written, S of f is equal to integral 1 2 over L 0 to L f x sin n pi x over L. This is how we have defined. Okay. So, here we need the sine transform of ut, u is a function of x and t, okay, u is a function of x and t. So, S of in place of f we shall write uxt, okay, this will be 2 over L 0 to L, in place of fx we shall write uxt sin n pi x over L dx. Okay. Now, if you want the sine transform of ut, ut is partial derivative of uxt with respect to t. Okay. So, this will be S of ut, okay, ut is equal to 2 over L 0 to L, in place of uxt now we will have ut. So, partial derivative of u with respect to t into sin n pi x over L dx. Since t and x are independent of each other, we can write it as 2 over L d over dt of 0 to L uxt sin n pi x over L dx. Okay. And this 2 over L we can take inside. So, we have d over dt of 2 over L 0 to L uxt sin n pi x over L dx, meaning that SUT is equal to d over dt of SU. Okay. This is d over dt of SU. Okay. Similarly, if you have SUTT, okay, in place of UT you have UTT here, then you will have UTT here. You can write d square over dt square outside, then SUTT will be equal to d square over dt square of SU in a similar manner. Okay. CUT, how we defined CF? Cn equal to CF we defined as 2 over L 0 to L fx cos n pi x over L dx. Okay. So, CUT we can similarly write CUT will be equal to 2 over L 0 to L ut cos n pi x over L dx, and this will be equal to d over dt of Cu as we have seen here. Okay. So, we get the same thing, and then here we also similarly get CUTT equal to d square over dt square Cu. Okay. Now, let us find S of uxx. Okay. S of uxx means 2 over L 0 to L second order partial derivative of u with respect to x. Okay. As I said, u is a function of x and t. So, partial derivative twice second order partial derivative of u with respect to x into sin n pi x over L dx. Now, what we do, we integrate it by parts. Okay. So, integration of by parts gives you 2 over L, integral of second derivative of u with respect to x, when you do, you get first order partial derivative of u with respect to x. So, u x into sin n pi x over L 0 to L, okay, minus 0 to L u x, okay, then derivative of sin n pi x over L. So, that is n pi over L cos n pi x over L dx. Now, you can see here, when you put x as L, sin n pi is 0, when you put x as 0, sin n pi is again 0, okay, and u x is finite quantity. So, this is 0, okay, this part becomes 0, and therefore, we have minus 2 over L. So, minus 2 n pi over L square 0 to 1 u x cos n pi x over L dx. Okay. So, we get this minus 2 n pi over L square 0 to 1 u x cos n pi x over L dx. Again we integrate by parts. Okay. So, integration of u x gives you u x t, okay, u x t cos n pi x over L 0 to L minus 0 to L u x t, then derivative of cos n pi x over L. So, minus n pi over L sin n pi x over L dx. Okay. Now, put x as L. Okay. So, u L t cos n pi minus u 0 t cos 0 is 1. Okay. Then here we have minus plus. So, plus n pi over L 0 to L u x t sin n pi x over L dx. Okay. Now, let us recall that cos n pi is minus 1 to the power n, minus 1 to the power n is the value of cos n pi. So, you multiply by this minus 1 inside. So, 2 n pi by L square you get, when you multiply by minus 1 you get u 0 t here, then minus 1 to the power n into minus 1 to the power n plus 1 into u L t. Okay. So, this we multiply to this, and then this minus 2 n pi over L square, when you multiply here, but you get minus 2 n pi over L square be multiplied to this. So, n pi over L 0 to L u x t sin n pi x over L dx. Okay. If you can write this, you can write as minus n pi over L whole square minus n pi over L whole square 2 over L 0 to L u x t sin n pi x over L dx. Okay. So, this is nothing but finite sine transform of u. Okay. So, we can write it as minus n pi over L whole square into S u. So, you can see this is minus n pi over L whole square S u. Now, you can see when you finite sine transform of u x x, when you find, it comes out to be in this form, okay, this one. Okay. So, here you need to know the value of u 0 t and u L t, the value of temperature at x equal to 0 and x equal to L at the two boundary points of the problem. So, we are given Dirichlet boundary conditions. Therefore, whenever Dirichlet boundary conditions are given, we use the finite sine transform to solve that problem. Okay. Now, let us find the Fourier finite cosine transform of u x x. Okay. So, finite cosine transform of u x x, if you want to find, then we know that cosine transform is given by C n equal to C f equal to 2 over L 0 to L f x cos n pi x over L dx. Okay. This is finite cosine transform of f. So, cosine transform of u x x. So, in place of f we are now having u x x. Okay. So, 2 over L 0 to L uxx cos n pi x over L dx. Integration by parts gives us 2 over L ux cos n pi x over L 0 to L minus 0 to L ux derivative of cos n pi x over L gives minus n pi over L sin n pi x over L dx. Then let us put the limits. So, 2 over L ux at x equal to L into cos n pi minus ux at x equal to 0, cos 0 is 1 and then this is plus n pi over L 0 to 1 ux sin n pi x over L dx. Now, this integral 0 to 1 ux sin n pi x over L, let us find differentiate by parts separately. So, 0 to L ux sin n pi x over L, when we integrate by parts we get uxt sin n pi x over L 0 to L minus 0 to L uxt derivative of sin n pi x over L gives n pi over L cos n pi x over L dx. Now, when you put x as L here, u is finite. So, sin n pi is equal to 0 gives 0 value, and when you put x equal to 0 again sin 0 is 0 and uxt is finite. So, we get 0. So, this part becomes 0 and what we get here, we get minus n pi over L 0 to L uxt cos n pi x over L, which can be related to the finite cosine transform of u. So, what you get here, this is 2 over L ux at x equal to L cos n pi is minus 1 to the power n minus ux at x equal to 0 and n pi over L here we have, and from here what we get, minus n pi over L and 0 to L uxt cos n pi x over L dx. So, and we know that from here 2 over L 0 to L f x cos n pi x over L is dx equal to C n. So, 0 to L u x t cos n pi x over L dx equal to L by 2. L by 2. So, this L by 2 we shall put for L by 2 C u x x. So, we will write L by 2 C u x x. No, L C u. So, sorry, L by 2 C u. So, we will get that. So, this you put here, for this you write L by 2 C u. So, let us see what we get then. So, 2 over L, we have 2 over L u x at x equal to L minus 1 to the power n in minus so 2 over L is multiplied to this as well as to this. So, 2 over L minus u x at x equal to 0. So, this is what we have and then minus n square pi square over L square. So, this 2 over L when you combine with 0 to L, this 2 over L when you combine with 0 to L u x t cos n pi x over L gives you this one C u. So, what you get is this. So, minus n square pi square over L square C u. So, this I can write minus n pi over L whole square minus n pi, this minus should have been here, this is actually minus n pi over L whole square minus n pi over L whole square C u minus 2 over L minus 2 over L, right, we have, because minus we have taken common. So, minus 2 over L and then u x 0 t minus 1 to the power n, minus 1 to the power n plus 1 u x L t. So, C u x x is actually equal to this. Now, consider the PDE, second order PDE. So, u t t plus u t t equal to u x x plus sin pi x. Okay. X varies from 0 to 1, t is greater than 0. So, we have a finite length. Okay. X varies from 0 to 1. We are given boundary conditions x equal to 0, at x equal to 0 u 0 t is u x t is 0, at x equal to 1 u x t is 0. So, we are given the Dirichlet boundary conditions. Okay. And when t is equal to 0, u x 0 is 1, and the derivative of u, partial derivative of u with respect to t. Okay. ut at t equal to 0 is given to be 0, okay, for all x between 0 and 1. So, what we do, let us take the finite transform of the given PDE. Okay. Taking finite transform of the given PDE means you multiply the PDE by sin n pi x over L and then integrate with respect to x over the interval 0 to L and multiply by 2 over L. Here we have 0 less than x less than 1, that means L is equal to 1 here. Okay. So, we multiply both sides by sin n pi x and then integrate with respect to x and multiply by 2 over L, that is 2 over 1. So, 2. Okay. So, 2 times 0 to 1 u t t sin n pi x dx, okay, is equal to 2 times 0 to 1 u x x sin n pi x dx plus 2 times 0 to 1 sin n pi x into sin pi x into dx. Okay. We multiply both sides by sin n pi x, integrate with respect to x over the interval 0 to 1 and multiply by 2 pi. So, that will give us the Fourier sine transform of the given equation. Okay. Now, we know that S of u t t is equal to d square s over dt square, we have seen it. Okay. So, left side becomes d square s u over dt square and then s of u x x. Okay. S of u x x we have already found. Okay. Let us see what is that. So, this is S of u x x. Okay. S of u x x is equal to this one, u 0 t is given to be 0, u 1 t is given to be 0. Okay. L is equal to 1. Okay. So, this is 0, this is 0, n is equal L equal to 1 means we get n square pi square s u. Okay. So, we get here n minus n square pi square s u. Okay. And then this is the last term, 2 times 0 to 1 sin pi x sin n pi x dx. Now, we know the property of sin pi x sin pi n x. Okay. They are mutually orthogonal functions. Okay. When m and n are not same, their integral over 0 to 1 will be 0. Okay. So, here you can see 0 to 1 sin pi x into sin n pi x dx, this is 0 whenever n is not equal to 1. Okay. And when n is equal to 1, we will get 0 to 1 sin square pi x dx, that value we can calculate separately. Okay. So, this is 0, this integral is 0 when n is not equal to 1, and when n is equal to 1 we get 0 to 1 sin square pi x dx. We can easily integrate sin square pi x, put the limits and see that it is 1 by 2. Okay. So, what do we notice now? We notice that this quantity becomes 0 when n is not equal to 1. Okay. And when n is equal to 1, this becomes half. Okay. So, we have two cases, this equation for n equal to 1 and this equation for n not equal to 1. Okay. So, let us see d square s u over dt square is equal to minus pi square s u when n is equal to 1. Okay. D square s u over dt square will be minus pi square s u plus 2 times 1 over 2. So, we will get d square s u over dt square equal to minus pi square plus 1. Okay. So, minus pi square s u plus 1. Okay. So, this is for n equal to 1. Okay. And then for n not equal to 1, this part becomes 0. So, we get d square s over dt square equal to minus n square pi square s u. Okay. So, this is the value when n is not equal to 1, this value we have when n is equal to 1. Okay. Now, by our definition of sine transform, by S u is nothing but S n t, and this is 2 over L 0 to L u x t sin n pi x over L dx. Okay. So, from here you can see if you put t equal to 0, okay, if you put t equal to 0, what you get? L is equal to 1 in our case. So, 2 times 0 to 1 u x 0 sin n pi x dx, okay, and what we are given u x 0 as u x 0 equal to 1, okay, u x 0 equal to 1. So, what we have S n 0 equal to 2 times 0 to 1, okay, u x 0 is 1 sin n pi x, and this we have already found earlier here, this one 2 times 0 to 1 sin n pi x over dx. So, this is 4 over n pi when n is odd and 0 when n is even. Okay. So, this is 4 over n pi when n is an odd integer and 0 when n is even. Okay. So, this value we know, right. Now, d over dt of S n t, when you differentiate S n t with respect to t, since t and x are independent, we have 2 over L 0 to L u t x t, okay, u t x t, and then you put t equal to 0. Okay. So, d over dt S n t at t equal to 0 is 2 over L u t x t at t equal to 0 into sin n pi x over L dx, and u t x t, let us see, u t x t is given to be 0. So, for all t. So, no, u t x t is given to be 0, u t x t is given to be 0 at t equal to 0. So, we have this, this quantity becomes 0. So, we get d over dt of S n t at t equal to 0 as 0. Now, then what do we get? Okay. This double dash means this dash actually denotes the derivative with respect to t. Now, we have ordinary differential equations. This is ordinary differential equation of second order, d square s over dt square equal to minus n square pi square s u plus 1, or you have d square s over dt square equal to minus n square pi square into s u. Okay. They are second order differential equations. Okay. So, what we have S 1 double dash t equal to minus pi square S 1 t plus 1. This is for the case n equal to 1. Okay. So, we have this, and the for n equal to 2, 3, 4 and so on, when n is not equal to 1, we have S double dash equal to minus n square pi square S u. Okay. So, S n double dash equal to minus n square pi square S n t. Okay. Now, general solution of this equation, this if you want to simplify, let us find the general solution of this. We have S 1 double dash, okay, t equal to minus pi square S 1 t plus 1. Okay. So, I can write it as S 1 double dash t plus pi square S 1 t equal to 1. Okay. So, this is of the form by double dash plus pi square into by equal to 1. Okay. And we know how to we solve this second order ODE with constant coefficients. Okay. So, we write auxiliary equation. Auxiliary equation is m square plus pi square equal to 0. Okay. So, m equal to plus minus pi I. Okay. We have complex roots. Okay. So, complementary function is a times cos pi x plus b sin pi x. Okay. Particular integral, let us find particular integral, we can find by 1 over d square plus pi square operating on 1, d is d over dt. So, I can write it as 1 over pi square times 1 plus d square over pi square minus 1 operating on 1. Now, this is 1 over pi square, we can write the infinite series expansion of this, d square over pi square plus d 4 over pi 4 and so on, okay, operating on 1, and d is derivative with respect to t. Okay. So, 1 over pi square, 1 into 1 is 1, all these derivatives, this second order derivative 1, this is fourth order derivative. So, they are all zeros. Okay. So, we have 1 over pi square. So, thus S 1 t, okay, the general solution S 1 t will be equal to a cos pi t, this will be t not x, because we have derivative with respect to t. Okay, so a cos pi t plus b sin pi t plus 1 over pi square. Okay, so we have this Sn t equal to S1 t equal to a cos pi t plus b sin pi t plus 1 by pi square. Now here let us see, when you put t equal to 0, okay, when you put t equal to 0, S10 is how much? A plus 1 upon pi square. S10 we found earlier, yeah, from here S10 when equal to 1, okay, S10 is 4 over pi, okay. So this is 4 over pi, S10 is 4 over pi equal to a plus 1 upon pi square. So a is equal to 4 over pi minus 1 over pi square, okay. And so we have found the value of a. To obtain the value of b, let us differentiate this equation with respect to t. So d over dt of S1 t equal to a is a times cos pi t. So a into minus sin pi t into pi, okay, plus b pi cos pi t, okay. So when you put t equal to 0, what we get? D over dt of S1 t at t equal to 0 gives you this is 0 b pi, but d over dt of Sn t at t equal to 0 is 0. This is valid for all n, okay. So d over dt of S1 t at t equal to 0 is 0. So we get this. So this gives you b equal to 0, okay. So this b is 0, okay. A is 4 over pi minus 1 over pi square. So we get the value of S1 t. S1 t is 4 over pi minus 1 over pi square cos pi t plus 1 over pi square, okay. Now let us find the general solution of the partial differential equation for other values of n. N equal to 1 we have solved. Let us find the value for solution for other values of n. So Sn double dash t equal to minus n square pi square Sn t, okay. So we have Sn double dash t plus n square pi square Sn t equal to 0. So this is of the form by double dash plus a square equal to 0, okay. So we know that the general solution is a cos a t plus b sin a t, okay, in this case, because right side is 0, so particular integral is 0, okay. So here Sn t will be equal to a cos a is equal to n pi, okay, a equal to n pi. So n pi t plus b sin n pi t, okay, this. Now let us see, we have Sn0 equal to Sn0 equal to, if you put n0 here, Sn0 is equal to c, okay. This is 1, so c, and this is 0. So Sn0 equal to c, and c is equal to Sn0 we have already found, Sn0 equal to 4 over n pi when n is odd, okay, and 0 when n is even, okay. So Sn0 is equal to, let us recall, 4 over n pi when n is odd and 0 when n is even, okay. N equal to 1 case we have already considered. So when n takes values 3, 5, 7, Sn0 is 4 over n pi, and for n even, that is 2, 4, 6, Sn0 is 0, okay. So this value is known to us. So this gives you the value of c. C is 4 over n pi for n equal to 3, 5, 7, 0 for n equal to 2, 4, 6. Sn dash t will be equal to what? Minus c pi sin n pi t. Oh, n also will come. So this will be minus c n pi sin n pi t plus d n pi cos n pi t. Now put t equal to 0. So Sn dash t equal to 0 is equal to d n pi, and see Sn dash t at t equal to 0 is 0. So we get d equal to 0, okay. So d equal to 0 for all n, all right. Now S and T is equal to then, so put the value of C 4 over n pi cos n pi t d is 0, and this is the value when n is 357 and 0 when n is 246. Okay. Now, apply the inverse sine transform. Okay. When you apply the inverse sine transform, you get u x t is equal to, okay, let us see that one, inverse sine transform. This is inverse sine transform. Okay. F x equal to sigma n equal to 1 to infinity S n sin n pi x over L is equal to 1 here. Okay. F x is u x t. So, we have u x t equal to sigma n equal to 1 to infinity S n t sin n pi x over L. S n t is 4 over n pi cos n pi t. We will write the value of S n t for n equal to 1 separately, okay, because that is separate case, this one. Okay. So, let us write that. So, u x t is equal to S 1 t is this one, 4 over pi minus 1 over pi square cos pi t plus 1 over pi square. Okay. This one. Okay. This is S 1 t into sin pi x, S 1 t into sin pi x, and then we write for odd values of n. Okay. This one, for n equal to 357, we put n equal to 2 m plus 1. So, then m will take values 1, 2, 3, 4, 5, 6 and so on. Okay. So, this will become 4 over 2 n plus 1 into pi cos 2 m plus 1 pi t, okay, and we multiply by sin n pi x. So, sin 2 n plus 2 m plus 1 pi x, okay, and summation will run over m from 1, 2, 3, 4 and so on up to infinity. So, we get sigma 4 over pi we can write outside, okay, 4 over pi, and then sigma n equal. So, in place of m now we have written n. So, 1 over 2 n plus 1 cos 2 n plus 1 pi t sin 2 n plus 1 pi x. Okay. So, this is how we solve the second order PDE by finite sine transform. Okay. Now, let us look at one more problem. Find the steady state temperature distribution u x y in a long square var of side pi. Okay. So, we have a long square var of side pi. Okay. This is of side pi. Okay. Long square var of side pi with one phase maintained at constant temperature u naught, u x pi equal to u naught. We have taken this phase, this is phase u x pi. Okay. This phase u x pi is taken as u naught, while other phases, this is u 0 y. Okay. U 0 y is taken 0, u pi y is taken 0 here, here u x 0 equal to 0. Okay. So, this side, this side, this side, these three sides are taken at 0 temperature, this fourth side we take at temperature u naught. Okay. So, one phase maintained at temperature u naught, other phases are taken as temperature 0. So, we have this in the steady state in 2 dimensions, we have this Laplace equation. So, u x x plus u y y equal to 0, x varies from 0 to pi, y varies from 0 to pi. When x is 0 means this y axis. Okay. So, u 0 y equal to 0, when x is pi, this phase, okay, parallel to y axis. So, this is 0 and then u 0 x, that is the segment on x axis. So, this u 0 x equal to 0 and then this phase is taken at temperature u naught. Now, taking the finite sine transform of the given equation, because here also we have Dirichlet boundary conditions. So, we multiply the given equation by sin n pi x over L, we take by as we are treating as t, okay, here. So, we multiply the given equation by sin n pi x over L, L is equal to pi here. So, sin n pi x over pi and then integrate with respect to x and multiply by 2 over L, that is 2 over pi. So, 2 over pi 0 to pi u x x sin n pi x over pi dx, then 2 over pi 0 to pi u y y sin n pi x over pi dx equal to right side is 0. Now, this is what since we have this S u x x, okay, S u x x. Let us look at the formula for that, S u x x. So, this is S u x x, okay, we are treating that by as t, okay. This t here is treated as by there. So, at x equal to 0 temperature is 0, at x equal to pi temperature is again 0. So, this is 0, this is 0. So, we have so this means that SUXX is equal to minus n square pi square over pi square, okay. L is pi. So, this is minus n square SU there. So, we get minus n square SU, this one, okay, corresponding to this term, and here this derivative with respect to y, second order derivative with respect to y, okay, can be written outside the integral because x and y are independent variable, and then we have d square SU over dy square, because as I said we are treating this by as t, okay. So, d square over dy square SU minus n square SU equal to 0, and this is equation is of the ordinary differential equation of second order with constant coefficients. So, auxiliary equation is m square minus n square equal to 0. So, m equal to plus minus n. So, we have two distinct real roots, and therefore, SU will be equal to a cos hyperbolic n by plus b sin hyperbolic n by. You actually we also write SU as a e to the power n by plus b e to the power minus n by, but we can convert it to cos hyperbolic sin hyperbolic functions, writing as a times cos e to the power n y is cos hyperbolic n y plus sin hyperbolic n y, and b as b times e to the power minus n y as cos hyperbolic n by minus sin hyperbolic n by. So, collecting the coefficients of cos hyperbolic n y and sin hyperbolic n by and using new arbitrary constants, we can write SU as this, okay. Now, since we are given since here SU is a cos hyperbolic n by, we are given ux0 equal to 0, okay. We are given ux0 when y is 0, okay, when y is 0 ux0, okay. So, this is x equal to 0, this is x equal to pi, this is this will be ux0 okay. So, ux0 equal to 0, okay, ux0 equal to 0. Now, what we have s of u is equal to 2 over pi 0 to pi ux by sin n pi x over pi dx, okay. This pi will cancel with this pi, we have 2 over pi 0 to pi ux by sin nx dx, okay. Now, put y equal to 0 here, okay. So, then this is a function of y, okay, SU is a function of y. So, actually we have S of uy there. So, S of uy actually we have. You can also write it as Sny. So, this is equal to Sny. When you take y equal to 0, what we get? Sny equal to 0 when y equal to 0, because ux0 is equal to 0. When you put y equal to 0 here, we are given that ux0 is 0. So, Suy, that is Sny is 0, okay. So, now this when you put here Suy, okay, this you put y equal to 0 here, we put y equal to 0, sin hyperbolic ny is 0. So, we get n cos hyperbolic ny is 1. So, A is equal to Suy at y equal to 0, which is Sn0, okay. So, Suy at y equal to 0 is equal to A, okay, but this is 0. So, we get A equal to 0, okay. Now, we have the other boundary condition y equal to pi, when y equal to pi for all x from 0 to pi ux pi is u naught, okay. So, this will give us the value of b, okay. So, here in this you put y as now pi, okay, A is 0, okay. So, S pi Su by at y equal to pi, this is given as u naught, and this is equal to 2 over pi, okay, 0 to okay, no, not this, we will have right side, okay, by equal to pi. So, b sine hyperbolic n pi. So, b equal to u naught over here sine su by at by equal to pi is not u naught, actually it is 2 over pi 0 to pi, okay. Then here we have su pi sine n pi x over pi. So, I sin n x dx, okay. So, this is actually u naught, है ना. So, 2 over pi u naught, and we have 0 to pi sin n pi n x dx, that we have to evaluate, है ना. So, b is 2 over pi 2 u naught upon pi times sin hyperbolic n pi, and then we integrate sin n x. So, minus cos n x divided by n 0 to pi, okay. So, this will give you 2 u naught upon n pi sin hyperbolic n pi 1 minus cos n pi, okay. So, this will be 0 when n is even, okay, because cos n pi will be 1, and this will be 4 u naught upon n pi sin hyperbolic n pi when n is even odd, okay, because cos n pi will be minus 1. So, so you replace n by 2n minus 1, okay, then n will run from 1 to infinity. So, u x y will be equal to we take inverse finite transform, okay, to write u x y equal to sigma n equal to 1 to infinity S n sin n pi x over L dx, okay. u x by equal to sigma n equal to 1 to infinity S n sin n pi x over pi d n pi x over pi. So, sin n x, okay. S n is this value, okay. So, S n is b cos sin hyperbolic n pi, and b we have found here. So, this is 4 u naught divided by pi, okay. Summation n is replaced by 2 n minus 1. So, that n runs from 1 to infinity. So, 1 over 2 n minus 1, okay, sin hyperbolic 2 n minus 1 pi, and then we have sin hyperbolic 2 n minus 1 by into sin 2 n minus 1 x, okay. Oh, here so we have found value of b, and then from b we find the value of S n, okay. S n is found from here after putting the value of b. Once we have S n here, we can then write inverse finite transform by u x by equal to sigma n equal to 1 to infinity S n n x sin n x, okay. And S u y, as I said, S u y is integral 2 over pi 0 to pi u x pi sin n x dx, okay. That is S n by, okay, this S n by, okay. So, from here we get the value of S n u is S n y. S n y, when we want to calculate S n y, okay, in order to get the value of b, we get the value of b is found from here by putting by s pi, okay. So, this is the value of this, then we get the value of S n, okay, S n equal to this. B is equal to, yeah, right. So, this is how we find the value of this. Now, so this is how we solve the second partial differential equation, Laplace equation. We in the case of a square plate, okay, whose one end is at u naught temperature, one face is at u naught temperature and the other faces are at 0 temperature. So, this is how we solve the equation. Thank you very much for your attention.